Right. So today we'll be discussing three practicals, right? One is based on a glass lab and the traveling microscope. Other two are based on prisms, right? Prisms and optical pins. So those are the three practicals we'll be discussing today. Okay, so this 16th practical, write down the topic, 16th practical, determination of, write down, topic, right? Determination of the refractive index, determination of the refractive index of glass using the traveling microscope, using the traveling microscope and a block of glass and a block of glass. Okay, so this is 16th practical in the syllabus, 16th practical, right? Determination of refractive index of glass using the traveling microscope and a block of glass, right? So for this practical, we need traveling microscope and a block of glass. Traveling microscope, we discussed that earlier. I'll just briefly explain what traveling microscope is, right? So here, in this practical, we are going to find refractive index of glass. So for that we need traveling microscope and a rectangular glass slab. So as I'm giving you this, you can take notes, right? You can take notes. Whatever on the board, you can take it down as well, right? So this is how the traveling microscope is. There's a base. Clearly listen, right? You have to understand the function of a traveling microscope, at least briefly here. So for the traveling microscope, it has a base like this. Base. This base should be horizontal. You can draw this with me. And there's two screws here to adjust the, so you can make this horizontal. To make sure that this is horizontal, there's a spirit level on this, right? Then there's this bar, metal bar. So on the metal bar, this is calibrated in millimeters. Then there's a vernier scale attached to that. Vernier scale, right? Attached to this. Actually, the vernier scale is attached to the microscope at the other side. This is a normal microscope, right? So through this bar, this vernier scale is attached to the microscope. Microscope is like this. So we look from here. We can change the orientation of this microscope, right? We can change that. There's a screw here. That screw is, let's say, screw 4. Then there's a screw here as well. To make horizontal adjustments, there's this is scale calibrated in millimeters, and there's a part here as well. That is the vernier scale. That part is vernier scale, right? That part is vernier scale. Quickly draw this one, and if you have drawn that, thumbs up. Right. Take this down, right? Take this down. This is the traveling microscope. Just a sketch of the traveling microscope. This is called horizontal scale, right? This is horizontal vernier scale. This is vertical vernier scale. So from these scales, you can read how much these are moved vertically and horizontally. You can move this bar, this microscope, horizontally and vertically. Then the distance you move, you can read it from these vernier scales, this one and this one, right? So there's a screw here as well, but this screw is not important for this practical. Using this screw, we can make horizontal movements of this whole thing, right? But this is not useful here. We only need this screw and this screw to make adjustments to this microscope. So what we do is we place the glass slab here. We place a glass slab here, and through the microscope we can look at the glass slab. We are keeping it vertically. Microscope. You can look at the glass slab. Then we can do our experiment. Right. So if you need, there's a small screw here as well. When you rotate that screw, you can move this whole microscope together. And you can adjust that. Then by rotating this one, you can fine adjust. You can move the microscope. By rotating this one, you can do fine adjustments of the microscope. You can do fine adjustments of the microscope. Okay, everyone taking it down? Right? Right. So before using the before using this traveling microscope, you have to do adjustments to this microscope, right? First thing is you have to make this base horizontal. So there are spirit levels, right? You have seen spirit levels, right? Like this. There's an air bubble inside this one. So you have to make it. You have to get it to the center. So when it gets to the center, we can say this is horizontal, and here is spirit balance. This is vertical. Once you do that, you have to do adjustments to get. You have to adjust this microscope to do the experiment, right? Then below this, right, adjustments. Adjustments in order. Adjustments in order. First one, write down first adjustment. Leveling base of the microscope. Leveling the base of the microscope. Leveling the base of the microscope. So you can use these screws, right, to do that adjustment. So there is a spirit balance on this base. Here it is not mentioned. You have to make the air bubble into the center when you adjust that. You can draw that from a side. This is called spirit level, right? Spirit level. Then second adjustment, adjusting eyepiece, adjusting eyepiece. Okay, adjusting eyepiece. For the microscope, eyepiece is this one. This one is objective lens. This lens is called eyepiece. First, you have to adjust the eyepiece. So to adjust the eyepiece, there is a cross wire inside the microscope, right? So if you get the microscope like this, here you have the eyepiece, right? Here you have the eyepiece. Then the another part, it includes the objective lens. So this is objective lens. Then there's the cross wires, right? Here it is, we have cross wires. Those are just two wires, right? Just straight wires. So by you can change the length between these two. By changing the length, you can actually focus cross wires on the eyepiece. Cross wires on the eyepiece. So then what do you see? When you look from here, what you see is a sharp image of the cross wires. Through the microscope, you should see this, something like this, right? So you have seen in, like, when you look through a sniper, right? There's a crosswire you see through that telescope there. This also has the same thing. So these are cross wires. So when you see cross wires sharply, then we can say eyepiece is adjusted. Eyepiece is adjusted. Right. Just draw these, right? Then third one. Focus the object by rotating, let's say this one A, by rotating screw A. Once focused, a clear inverted image can be seen on cross wires. A clear inverted image can be seen on cross wires. Right? So then the next step is you just have to focus this microscope. You can do that by rotating this screw. When you rotate this, whole microscope moves up or down, right? So depending on the distance, so when you place the object here, you can change the distance to that object from the microscope and focus the microscope, right? Then what you see is a image on this, object on this microscope. Image of the object on the microscope, and it is inverted, right? Right. So now the adjustments are done, right? Then the first thing you have to do is, so this is the base of the traveling microscope, right? You can just take a piece of paper and put a mark there and place it on the base. Then you can focus the traveling microscope. I'm just drawing a part of that, right? Traveling microscope here. You can focus this, you can put it like a cross mark here. You can focus the cross mark from the traveling microscope. Then the traveling microscope has this main scale and a vernier scale. So from the vernier scale, you can get the reading. Let's say R1. So this is the lowest point, right? Okay. Then using those screw at the side, by rotating that, you can lift this microscope, whole thing, right? But at the second case, you have to place the glass slab. You place the glass slab. So at the bottom there is still that mark is there, right? So what happens to that mark? It has an apparent displacement. Now the object is here. It has an apparent, let's say, now the image form of this object is here. So we call this distance apparent displacement. Apparent displacement. And this depth, we call that apparent depth. You can take this down. This is called apparent depth and this is called apparent displacement. It is upwards. And this is the real depth, right? Real depth. Now, you have to focus the microscope not to this object, but to this image. Right? To this image, you have to focus that. So to focus that, it is clear. To focus that, it is clear that you have to lift the microscope, right? So using that screw A, you have to lift the microscope. So it is lifted, right? And again, you can take the reading there. So this is the main scale reading, then the vernier scale reading. Let's say that reading is R2. Okay? That reading is R2. So this microscope is focused to image. Right? Image here. Then you need to get the real depth. You need to get the real depth. To get the real depth, what you do is, you have the same glass slab. You have to sprinkle a little bit of lycopodium powder, right? Lycopodium powder onto the glass slab. Then you focus the microscope to the lycopodium powder. So to focus that, you have to further lift the microscope using that screw. Let's say you lift this to here. Then you take the reading here. So let's say that reading is R3. This reading is R3, right? Take it down. And this is called lycopodium powder, right? Lycopodium powder. Take it down. Right? Okay, now we have 3 readings, right? 3 readings. So from these readings you can find, so the goal here, in order to find the refractive index, you need to get real depth, which is the thickness of the glass slab. Apparent depth, those is stuff, right? So as I'm writing, take notes. Real depth is what? Real depth. This much is the real depth. Here it is focused to R1. Here it is focused to the top of the glass slab. So R3 minus R1 should be the real depth, right? If you don't understand, let me know. R3 minus R1 is the real depth or the thickness of the glass. Then we need apparent depth. So what is the apparent depth? This much is the apparent depth. Okay, so how do we find that? Here, at this case, microscope is focused to the image. Here it is focused to the top of the glass slab, right? So if you R3 minus R2, R3 is here to the top, R2 is to this here. So R3 minus R2 should be the apparent depth, right? Take it down. Apparent depth is R3 minus R2. Then you know that theory. Refractive index of glass relative to air, because it is at air and we are finding the refractive index of glass, right, is equal to what? Real depth divided by apparent depth. NAG is equal to real depth divided by apparent depth. So this becomes the refractive index of glass. Then you can, since you know these values, you can simply substitute them. So real depth is R3 minus R1. Apparent depth is R3 minus R2. Okay, take it down, and once you take it down, thumbs up. There's an issue with the Zoom, right? I'll just turn it off now, and I'll send you the link again, right? Then join. Just give me like 2 or 3 minutes, okay? There's an issue with the Zoom. I'll send you the link again, right? Then join again. There's an issue with the Zoom, right? Right. Okay, so in this method, you can find refractive index of glass, right? Using the traveling microscope. So this is a very accurate method because traveling microscope is a very accurate measuring instrument, right? So these lenses are very accurate. So from this method, you can find the refractive index of glass, right? Right. But the thing is, here we did only one calculation, right? We have done only one calculation. Just a one direct calculation, you found this. Not a graphical method. We didn't go for a graphical method. So in a case like this, there could be random errors. Random errors could be larger in this case. Somewhat, if you need to decrease the random errors, you can take 3 values for refractive index. Let's say you got N1, N2 and N3. These are 3 close values, and you can get the average, right? So how do we get 3 values here? You know that this is a glass slab, right? So the glass slab has, if you think about from here, so this is the glass slab, right? Right? If you place the glass slab to this side, like this, then you can get the measurements along this. So using this, when you look from above, you can take a 1 value for refractive index. Then what do? Then you can flip this glass cube and do the experiment to this side, right? Then again do the same things and find a value for refractive index. Then you flip this like this, right? Then again you do the same steps. Like that, there are 3 different sides in a glass slab, right? So along those 3 different sides, you can do the experiment 3 times and find a value for refractive index. Then those 3 values, you can divide that by 3 in order to find the average, of the refractive index. So that would decrease the random error somewhat, right? Okay. Now the practical is over. Then we'll move on to some discussion points, right? Write down the first point. These are discussion points, right? As I'm telling, as you are reading, you have to understand what I'm saying here, right? Okay, take it down. If the glass slab is rectangular, comma, using its 3 sides, with different thicknesses, find 3 values for refractive index of glass. So if those values are N1, N2 and N3, so the average is this one, right? You can take this down. So this is a more accurate value for refractive index. Below that, right, this decreases the random error. Right. Then another point, take it down. The same method can be used to find refractive index of a liquid. Right? Okay. So let's say you have a beaker here, right? As I'm drawing, you can take this down. You have a beaker, right? And at the bottom of the beaker, let's say you have a pin, optical pin, it could be optical pin. Then you need to focus. It is the same method, right? Focus the microscope and get the reading from the vernier scale. Let's say that reading is R1. Then you fill, let's say, the liquid up to somewhere here. So then what happens? This is the object, right? Then due to this liquid, image of the object gets a apparent displacement upwards. Somewhat like this, right? So after that, what you see through the traveling microscope is the image of the optical pin, not the object, right? It is already lifted up. So to focus this one, what you have to do, you have to lift this microscope. So to lift that, you can use that screw, a screw. Again, let's say you lifted it up to here, and once you lift it, you can get the reading. Let's say that reading is R2. So now you have focused it here, right, to the image. Then what do? Now you need to take the real depth. So to get that, you have to put lycopodium powder. You have to sprinkle lycopodium powder onto the liquid. The specialty about lycopodium powder is it does not dissolve in just water, right? It doesn't dissolve in water. So you can put lycopodium powder and it floats. So to focus on to lycopodium powder, you have to further lift this microscope and then get the reading. That is R3, right? Similarly, N is real depth divided by apparent depth. So what is the real depth? This much is the real depth. So real depth can be taken from R3 minus R1. So that is the real depth. Apparent depth, this much is the apparent depth. So that is R3 minus R2. R3 minus R2. So these values you know, then you can simplify the refractive index of liquid. Refractive index of liquid, right? We don't stop here. For the liquid, we can use a graphical method. We can use a graphical method because the thickness of the liquid or the real depth of the liquid, you can easily change. You can put more liquid onto this, right? And change this real depth. If you take 6 different real depths by pouring more liquid onto this, then you can draw a graph. Right, so let's see how to draw the graph. Just take this to the other side, R3 minus R2. So R3 minus R2, cross multiply, right? To take this to this side, put n to the other side. Then 1 over n, R3 minus R1. Right? So R3 minus R1, what is that? R3 minus R1 is the real depth. That is the variable we change, right? By pouring water, you can control this variable easily, right? So that variable is what we call that independent variable, x. This is the what we change first, right? So depending on that, apparent depth changes. This is the apparent depth. Or R3 minus R2, apparent depth. This is the real depth. By pouring water, you can change the real depth. That is R3 minus R1. Because we can change that first, right? Depending on this one, when you change real depth, apparent depth changes, right? So this apparent depth is dependent on this variable. So we call this one y. So we have a y equals mx graph. Then you can get a bunch of readings for this. You can draw a graph, y equals mx graph, and from the gradient, you can find 1 over n. So this is a more accurate method. But we could do this for the liquid, right? Because we cannot change the thickness of a glass, but we can change the depth of a liquid easily. For the glass, we cannot do this. That's why earlier we couldn't go for a graphical method, right? But in this case, we can. Okay, take it down and thumbs up if you have taken it down. Right? Okay, so at the home, you can try this question, 2018 A-level question. This is homework, right? 2018 A-level question. That is a easy question. Once you do this, once we discuss this experiment. So this is the homework, right? Okay, so that is everything about how to find the refractive index using traveling microscope and a glass slab, right? Then